It's my absolute pleasure to introduce Jan Fuhg, who is a dear colleague of mine, and we're very honored to have him. He's going to be speaking about his recent work on the quest for physics-augmented neural networks for parameterized polyconvex materials. Somehow I'm finding my name on here. I'll be curious to find out what I did for this. But all joking aside, we appreciate you. Thank you very much, and you'll get signals from me.
Thank you. The more I look at the title, I like it less and less. Maybe I should have stuck with the original one. There's a joint work with a lot of people, and I put Adrian as UT Austin because I think both Manuel and me, we are still in denial that he's going to leave. So we're going to have it in history that he was actually here. This is kind of work that is driven by people at Sandia. Reese, who's going to give a talk in like an hour or so. And my student, Aska, who's given a poster later. What we are primarily interested in is, given the recent rise in novel manufacturing techniques, we can suddenly create microstructures a lot quicker than we can keep up in calibrating them. So when like 15, 20 years ago, people could spend their whole PhD coming up with a single phenomenological law for a specific form of rubber, now we can create 15 rubber microstructures in an hour. We can't spend 5 years again to come up with a phenomenological law. And the main interest of this is if you can create 15 microstructures in an hour, you can also parameterize them. And then you can solve inverse problems to find out what is the best microstructure for a given response that you're interested in. And then we would be interested in finding parameterized constitutive models. And this is where current phenomenological laws that are just based on three parameters really fail. So that's why we come up with kind of neural network approaches to this. I'd like to kind of introduce PANS or PANS. We get a lot of trouble for this name because people always confuse us for pins. But the main difference is that in constitutive modeling, we have a data regime which is very limited. So this is probably the easiest data case for nonlinear elastic material. So we have a form of invariant at the bottom, at the x-axis, and another invariant at the y-axis. And what you would usually get, and people have calibrated material laws for 50 years, is in this kind of space that you get, you just see data on this uniaxial kind of functional. And you don't see anything else. Sometimes you're lucky and you get equibiaxial data, but this is very rare. The problem is that we calibrate our models based on this data, and then we use the actual models in finite elements applications, and then we see all the space. So we are in a data regime where we cannot learn anything really explicitly, but we want to put as much implicitly into it. And Adrian alluded to that we kind of use PANS for that, which implicitly fulfill a lot of physics. So it's kind of my outline. I want to say kind of the requirements that we have or that we know that we can fulfill out implicitly. And I want to give a primer on this kind of standard physics-augmented neural network that people have been using for the last 2-3 years. And then a couple of ways how we have recently trying to extend it to account for different physics or take a look at constitutive modeling from a different angle. So I'm primarily focusing on nonlinear elastic materials. So Adrian was talking about hyperelasticity, for example, where you have a free energy function that is a function, for example, of the deformation gradient, the temperature, some structural tensors and internal variables. We have a big requirement on that, which is polyconvexity, and Adrian was talking about that, where if we have only mechanics, we need to be convex in the set of minus of the deformation gradient. And if we then add temperature, we also need to be concave in the temperature. And kind of these are the requirements that I'm going to be focusing on here. If we add dissipation to it, so plasticity or viscoelasticity, we can add a different potential, which then has very similar requirements. So if we can find implicitly neural networks that implicitly have restrictions like convexity and restrictions on the first derivatives of the function that we're looking at, we should be good for a wide range of materials. And kind of the workhorse for the last couple of years were partially input convex neural networks. Okay, the convex is already in the name. What you essentially get is you have two branches of inputs. You have a free branch and a convex branch. And there's a wide range of ways to guarantee convexity. These kind of networks make it very easy, because essentially you have in the convex branch, you want to be convex to x, or the output needs to be convex to x. And you can do this by enforcing that all these weights here in red are positive, and you have specific constraints on the functional form of the activation functions. And that's something that you can very easily do in your optimization process. Okay. For hyperplasticity, these are the ideal 9 requirements that we want to have fulfilled. I'm going to go over them one by one a little bit. But polyconvexity is, for example, here one of them. The other big one is the normalization of the stress. So if we are in the undeformed state, we want also in the undeformed state, we also want zero stress. And some other ones that we can easily fulfill by switching from a primary deformation gradient to invariant space. So what does it look like? So assume we have isotropic hyperplasticity. We have 3 invariants as an input. So we can switch from our neural network, which takes the deformation gradient or the right Cauchy-Green stress as an input. And we can write it, instead of doing that, we can write it as a function of the invariance, and we can derive the stress in classical ways. And if we then just use this neural network, we would already have fulfilled 4 of the requirements that we have. Okay, just by having an easy input switch. We can then subtract the energy that we would have in the undeformed state, and we would get a normalized energy. We can do something similar for the stress. We can add a component for the growth condition. And now is the interesting part with the polyconvexity. We would need to be, in order to fulfill polyconvexity and isotropic hyperplasticity, we would need to be convex and monotonically increasing in I1 and I2, and convex in J. Okay? So we have this neural network, which we could now, for example, switch out to an input convex neural network. The problem is that we can only fulfill, with the current standards, input convex and monotonically increasing neural networks. Okay? We can't have some of the inputs to be just convex and some to be input convex and monotonically increasing. So our way around it, and that was kind of like proposed 2-3 years ago, was to add an additional input, which is also convex in J, which is minus 2J. And then we have now, instead of 3 inputs, we have 4 inputs, and we have an input convex and monotonically increasing network by also having basically all remaining weights of our partially input convex neural network also being positive. We need this additional input because otherwise we can't get a negative stress. If we have only I1, I2, and J and are monotonically increasing and convex in I1 and 2 and J, we can't get a negative stress value. So we need to add a new input. And this is kind of what we get out of that. If we have general data, this case is the red dots is a Treloar data set. We have uniaxial tension data. We have equibiaxial tension data in blue. And we train on both of those. And then we test on the green data set, which is pure shear. Okay? And on our left-hand side is if we use a standard neural network formulation, no implicit physics, we still take the invariance as input because it's a bit easier. And then on the right-hand side is if we would take our just derived physics-augmented neural network. And we see that we fit the data a little bit worse. But what we definitely do is we have a lot better generalization. Okay, just implicitly in the network. And we then can extend that to parameterizations. So now we can add some form of parameter delta that we can take as an additional input and can then use our partially input convex neural networks that are now also convex and monotonically increasing in these other inputs to have a free branch and a convex monotonically increasing branch, and can now train parameterized polyconvex problems. So for example, if we have a range of microstructures given by some porosity or void fraction and like some shear modulus, we can train them all at once and then do informed decision about inverse problems. Okay? So this is all working rather fine. The problem is when we need to extend it to other things. Okay? And that was kind of our first hurdle like a year ago when I started. What if we have thermohyperelasticity? And in thermohyperelasticity, we have an additional input, which is the temperature, which we now need to be concave to. Okay, so now we have a problem because we only have convex neural networks. We don't have concave neural networks. Okay, and I was looking at this for like probably 6 months before we actually started at it. Reese and I were talking about this. We were trying to get an input convex, input concave neural network to work, but we couldn't. And I don't think it's possible. So we had to come up with something else. And the way we're doing it is some representation theorem thing, where we take the sum, a convex sum of components related to the mechanics. So in this case, the psi's, and then some components related to the temperature that are multiplicatively added to it. So essentially, we have this phi of t times a psi, which is then just a function of the mechanics. And then we have what we call the polyconvex concave network, where we need to be positive and convex non-decreasing in I1 and I2, and convex in J, which are these psi 0 and phi i's. And in the phi's, we need to be positive and concave. So now we know how to deal with this. We don't know how to deal with this, so we need to come up with a positive and concave neural network. We still need to carry over the minus 2j, because otherwise we can't get negative stresses. But then we came up, and this is rather simple. This should not be convex, should be concave. By, again, just assuming that weights and biases are positive and some restrictions on the activation function, which can, for example, be fulfilled with sigmoid, we can come up with a guaranteed way to have a positive concave neural network, okay, that we can then use in this formulation. And you can, for example, see here, it can easily fit concavity, and if we have actually something that is convex, we fail and we just have a line. Okay. And we can then use that, for example, on actual experimental data. This is like, I think, Pig. And this is like incompressible. And we can, again, do energy normalization, stress normalization terms. Can then do some sparsification to counteract that we have so little data. But then we fit this quite well, and we also generalize quite well. Okay. The next part, and that's where Adrian and I, and that's why also Manuel is on this slide, is that there's a wide range of hyperelastic laws, for more specifically the Oden model, which is not dependent on the invariance or the classical invariance of the strain. It's dependent on the principal strains. Okay? And a lot of people in biomechanics, they really like the Oden model. I don't know why, but they're really into that. So we're trying to figure out, instead of having an invariant formulation, can we do a principal strain formulation as a physics-augmented neural network? Okay? The problem is we run into a different constraint. Okay? So Before we were convex in J and then convex monotonically increasing in I1 and I2. Now if we write our minus in terms of the principal strains, we end up with something that's a little bit more complex. We need to be convex in all the principal strains separately. They're like multiplicative doubles of the principal strains and the deformation, like the J, the determinant. Okay? Additionally, we need to be permutation invariant in this thruple and this thruple separately. Okay? We know how to do convexity. We don't know how to do permutation invariance. And that was kind of Adrian's and my problem for like beginning of this year, how we can kind of do this. What we found was, the thing is what we do, computational mechanics people, we don't really know computer science that well. We look at people who have done already, that they have applied to their MNIST data sets, and we hope we can apply it to actually our interesting things. So one of the things that we found was the Hölder power deep set, which if you have 3 inputs, you have one function that you need to fit, which could be a monotonic input convex neural network, and then another input, which could be a positive input convex neural network. But if we represent something like this, then you are convex in x1, x2, and x3, and you're permutation invariant in x1, x2, and x3. Okay? And then we try to apply this idea to model kind of hyperelastic materials. And this is the rather complex looking thing that we came up with. What I want to highlight again that we need to have both J and minus 2J as inputs, otherwise we can't represent negative stresses again. Okay? We have essentially one block that deals with the convexity and the permutation invariance to lambda 1, lambda 2, and lambda 3. And then we have another block which deals with the convexity and permutation invariance of these like doubled multiplicative terms. Okay? And then we combine them all again in a monotonic input convex neural network to represent it. Okay? And it looks complex. We can choose all these networks very shallow, and it actually works quite well on very limited data sets. Like, again, this is like rubber data, where we train it on the blue and red points, so it's like 20 data points, and we test on the green. And it seems to be working fine for different data sets again. Okay? This was what Adrian and I and Manuel were working on. I was always bothered by this minus 2J. Okay? I didn't like that we need to extend our input size because we don't have a way of dealing with convexity and convex monotonically increasing separately in a network. Okay? If we increase our input dimension, it also means we need to have more parameters. And the training is going to be more expensive. And it seems to be easy, or it should be easy to come up with something that would avoid that. So I put my student on this, and he came up with something that I'm kind of a fan of. The reviewers of CMAME didn't like it as much. But we are hopeful that we can convince them. But we came up with what we call input-specific physics-augmented neural networks, which looks a bit more complicated. But essentially, instead of just having a convex and arbitrary branch, we now have a convex branch. We have an arbitrary branch. But we also have something where we have inputs that are just monotonically non-decreasing, so like increasing, monotonically increasing. And then we have another branch which is convex and monotonically non-decreasing. Okay? So now we can choose whatever branch we want. We can use these inputs. And we can fulfill implicitly just by selecting positive weights and specific activation functions. All of these constraints can be put into one neural network formulation. Okay? And now we see that we actually have a way to get rid of this minus 2J because we can put I1 and I2 into the upper branch, which is convex monotonically non-decreasing, and then the j into the convex branch. Forget about all the other ones. Just pretend they're not there, because they're easily just replaceable. And then we have a network that is hyperelastic, and we can do all of this stuff. Okay? Now, additionally, if we have a parameterization, like a microstructure parameterization, we can now also add arbitrary parameterizations or parameterizations that are monotonically increasing or parameterizations that are convex, automatically fulfilled in this neural network architecture. Okay? My student went a bit overboard. This is not an easy way of writing this out. I mean, it's like 4 lines, but normal partially input convex neural networks, when you first look at them, they're not that easy to understand. This is a bit more complicated. But he derived analytical expressions for the first and second derivatives, regardless of the width and input dimensions. Okay? Why is this important? Because we have the problem in computational mechanics that our networks should be, or if we do constitutive modeling, that our networks should not only be stand on its own, but they should eventually be incorporated into a finite element or whatever partial differential equation solver. And there are oftentimes commercial tools. And commercial tools don't have AD capability. Okay? So oftentimes, if you write something in Abacus, you would need to hand derive your first and second derivatives for the Hessians. Or you would need to do finite differences, which, if you have like 10 inputs, you don't want to do that. But so what he did, he wrote, it's like 5 pages just of first and second derivatives of these networks. And we can then show that if we use the same things in PyTorch, for example, we are a lot quicker if we do this manual differentiation than if we do automatic differentiation. And we can then put these networks into our tools without needing to have AD capability to come up with like higher order derivatives. The other thing that I like is that we have the issue in kind of homogenization, that even if we have a microstructure, let's say this is some fiber microstructure, even if all the individual faces have polyconvex, let's say hyperelastic laws, the homogenized response does not need to be polyconvex. Okay? So we can fit hard-encoded polyconvex response to this RVE, but it might not be a very good fit because the RVE response might not be polyconvex. Okay? And it was a bit of an issue because then how would you know if you should use a polyconvex network or if you shouldn't use a polyconvex network? Okay? So what my student did, he came up with this kind of gating concept, which kind of lets the network decide itself if it should train something as polyconvex and non-polyconvex. Okay? The way we do it is that we always prefer polyconvexity. Okay? If we can guarantee polyconvexity, that's the best case scenario. In case the network doesn't train or doesn't like it, we go into a free branch. Okay? If one of these branches drops out, so if, say, the input or the network decides that it's no longer, or the data does not reflect a polyconvex condition, all the weights and biases that are relevant for that go to 0, and we only keep necessary weights and biases. We don't even need to store the ones that are gated out. And then can put that back into a commercial FE code, for example. So we can, for example, look at this. This is a transversely isotropic RVE with a preferred direction. And we can train on that. And we find that this is the loss. We have, at the beginning, we have both polyconvex and non-polyconvex inputs active. Then at some point, the polyconvex part kind of gets activated because we would prefer polyconvexity. But then at the end, the network decides, okay, the best way to train this is with a non-polyconvex neural network. And this is all automated. And we tried this out on all kinds of RVEs and analytical laws, and it always seems to be finding the correct one. And that concludes, I think I'm right on time, my talk. I want to kind of like give different extension to PANs that we have been working on, where we felt like we couldn't just use standard input convex neural networks. And I think, again, I hope maybe the reviewers see this. We think that input-specific neural networks offer a new dimension, that they offer something that is actually novel, which they didn't think. And if you're interested in the paper, please have a look at the QR code. Happy to answer questions.
So earlier we spoke about the MNIST challenge. I have a third challenge. If you give a talk in which you mention convex more often than Jan, you win an award, a big one. Michael, I'll come over and find you.
Give me my water.
I was trying to think of some joke about the words pro and con and convex, but I can't think of anything. So anyway, it should be possible, since convexity and polyconvexity are formally defined mathematically. Okay, and this kind of goes back to the other problem you have in defining that. And, you know, it's not necessarily built into the form. It often boils down to restrictions on parameter values and interrelationships. And if you can establish that, you can hard code that into the neural network as either constraint or other forms that you can do. And that way, what you get out of it is an almost guaranteed convex forms. And these can be very subtle when you're dealing with tension, compression, nonlinearities, and shears and various combinations. And I think that this goes back to my previous comment that the other aspect is making sure you have the right, I would say, lack of a better term, data to train it on. Because it may affect, for example, if you're doing an organ simulation, you know, how you deform that organ in one way versus another to get that out. I don't know just what you thought about that.
I mean, the problem with, the computational mechanics community for like the last 20 years has really embraced polyconvexity, but it's kind of like over-constrained. The problem is that the like simpler or kind of constraint we actually want is like an integral form constraint with quasi-convexity, which we can't get guaranteed. At least so far, no one has figured out how to do this guaranteed in any way in any hyperelastic law. So then they use the next strongest one, which is polyconvexity, which also guarantees quasi-convexity. But that's why probably we're seeing that if we actually have experimental data, which of course doesn't need to be convex because there's some noise in there, or our homogenization responses, polyconvexity seems to be too strong. It is nice mathematically, but it's probably for a lot of things maybe a little bit too strong. But if we can guarantee it, it's a very nice thing to have, because then things converge very quickly and we can choose. You don't agree? Okay.
Any other questions? Back here.
Thank you for your presentation. I have a very simple question. The thing is that you're talking about considering minus 2j in order to have a negative stress. But you finally concur that we can omit minus 2j in order to again get the negative stress again. I didn't catch exactly what happens here that you can consider this negative part. Thank you.
So the issue was that if we have if we have I1, before we had I1, I2, and J as inputs, and we only had networks that we could only be convex and monotonically increasing at the same time to a particular input. We couldn't be convex and monotonically increasing to some inputs and only convex to others. Okay? There was no network architecture out there, at least no one has found one, I don't know, that would give you that. Okay? And if you can only do convex and monotonically increasing, then if you are convex monotonically increasing in I1, I2, and J, you cannot represent negative stresses. So then you add minus 2J, which is also convex in J, which is what you need for polyconvexity. But by adding the minus 2J, you get back the ability to get negative stresses. But now with this network architecture, we can actually be convex to some inputs and convex monotonically increasing in others. So then we can go back to the original actual formulation instead of needing to add minus 2J to it.
Awesome. I think we're at time. So let's thank Jan one more time.